Hello everyone, welcome back to the latest session. Let's continue looking at the most prevalent groundwater pollution problems that Indians face, right? So we were looking at contamination of water by iron, right? And I think fluorides, salinity, let's say, right? And what else? I think nitrates, right? And then we are moving on to contamination of groundwater by arsenic. And this is an issue because it can lead to acute and also long term issues too, right? As in it's both toxic and also carcinogenic, right? It can also lead to cancer. So again, what are the hot spots? West Bengal, I guess, and some reaches of Uttar Pradesh, and some in Punjab and Haryana and in Karnataka. But again, the issue is that it's remarkably what do we say, toxic and carcinogenic. As in, if we just switch back to the relevant BIS standards that we looked at earlier. Again, what is this? This is the drinking water standards, I guess. And here we have different limits for different parameters. Here we are talking about concerning, these are the general parameters concerning substances which are undesirable in excess amounts. So, for example, we are looking at nitrate 0.3 milligram per liter, right, and nitrate 45 milligram per liter, and so on and so forth. But with respect to arsenic, you see that it is listed under parameters concerning toxic substances, right, as in it can lead to different forms of toxicity in humans, or it can also lead to carcinogenicity, right. And what do we have out here? Where is this arsenic? Well, let's hope I am not mistaken. Here we have total arsenic, but typically in different countries you have arsenic 3 and arsenic 5, specification or standard for arsenic 3 and arsenic 5, 0.01 milligram per liter, let's say, right. So that's 10 ppb, I guess, right. So let's go back to where we were. So here we have limits for of acceptable and permissible limits up to 0.05 milligrams per liter, and red is where we have arsenic greater than 0.05, I guess, right. West Bengal, and what else? Uttar Pradesh and Karnataka, and even near Delhi, I guess, right, NCR, Delhi. And let's see what are the effects, obviously. So some chemical background or chemistry, I guess. Arsenic 3 is relatively less soluble, and obviously it's less soluble, meaning it's typically in solid form, and it's immobile also, right. It's relatively immobile. But arsenic 5 is highly soluble, right. Arsenic is 5 is highly soluble and thus mobile. And in India we also have deposits of arsenic 3 or arsenic, and that can lead to what do we say, groundwater pollution due to arsenic. And what do we have here? I guess, yes, this is what I was trying to lead to. Overexploitation of underground water causes the geochemical leaching of arsenic from arsenic bearing rocks, right, into the groundwater used for drinking purposes in many places in India. Okay. So what happens is, let's say you have arsenic in number 3 form or oxidation state 3, let's see, right. And when you have what do we say, the groundwater from that area being pumped out and it being replaced by groundwater from other regions that has, let's say, maybe not groundwater or water that has that now comes in contact with oxygen, or the rocks itself coming in contact with oxygen, let's say, you are going to have oxidation of arsenic 3 to arsenic 5. And obviously, as we see, arsenic 5 is much more soluble and thus mobile, let's say, right. So that's an issue again due to over exploitation of groundwater, right. So it's not pretty straightforward, but obviously depends upon human usage too, right. Obviously you need to have arsenic deposits out here, and it is by far one of the most toxic substances found in groundwater, and that's the case even in the US and other countries too. And ingestion of arsenic at 10 ppb, right, 10 ppb or 0.01 ppm or 10 parts per billion, parts per million and parts per billion, causes severe disorders. So pigmentation in the skin followed by lesions and damage to the internal organs, causing cancers, and can or usually or quite often becomes fatal. As I mentioned, it has both toxic effects and depending on the dosage and such, also carcinogenic effects, right. So, that is what we have, right, different what is it, pigmentation on the skin and so on and so forth. Yes, and in India more than 7 states have dangerous levels of arsenic, often in the range of 100 to 500 microgram per liter or 100 to 500 ppb, 10 to 50 times the regulatory limit, right. So, that is something to keep in mind. So, typical water quality parameters, we look at these parameters in greater detail, right. And two aspects, obviously one to keep you informed, the other is that if I keep talking about generic stuff, we see that the students' interest tapers off. So, we need to have some calculations, and I guess here we are going to try to introduce some calculations, while obviously keeping you knowledgeable about the relevant aspects, right. So, here we have typical water quality parameters. Here now we are going to talk about turbidity, which is a measure of suspended solids and total dissolved solids. So, I guess turbidity, this is what typical surface water can look like, right. Suspended solids, can you drink this? Not really. So, obviously direct hazard to aquatic life, can cause anaerobic conditions. Siltation, in reservoirs reduces the capacity, and in wastewaters, it gives you an idea about how polluted the water is, because if it is sewage, you can have, what do we say, organic suspended matter too, right. So, let me go ahead and look at estimate of biomass and so on and so forth. We will not look at this for now. Drinking water, we use turbidity in terms of instead of total suspended solids, but what is the issue? Aesthetics, obviously people do not drink this or will not drink this, and the other issue is that suspended solids, they act as carriers of either inorganics or more importantly of pathogens, right. You have nooks and corners, and in these crevices and such of the suspended matter, you are going to have pathogens thriving now. So, that is why suspended matter, rather than though they are harmful by themselves, right, you are also going to have them acting as reservoirs of pathogens. So, that is one thing to keep in mind, and obviously they interfere with other water quality treatment processes, right. So, suspended solids, you have volatile, right, measured by which measures the organic what do we say forms, which is algae and bacteria. Inert, and generally for it is used for wastewater. Suspended solids being 0 is clear groundwater, right, but again as we saw even in Haridwar, the groundwater was not really clear. That means there was some pollution out there. For sewage, for monsoon rivers, because of why is it relatively high in monsoon surface waters or surface waters during monsoon? It is because you have all the rainfall bringing this runoff and thus the sediments and such to the river, right. So, you are going to have that high, and food industry wastewater, obviously it is going to be remarkably high. So, what is the issue here? So, when it is 0 to 50 ideal drinking water, but 50 I guess is a bit too low, I would say so. And how do you achieve this? This is after treatment by reverse osmosis, distillation, deionization, microfiltration. Again, before reverse osmosis, obviously you need to have micro and nano filtration. So, again 0 to 50 you need to have treatment, I guess. 50 to 140, as I mentioned, is considered acceptable range, but again it is from carbon, after carbon filtration and mountain springs and aquifers. This is what we saw, I think, in Joshimath. Less desirable, and this is unpleasant water from tap water and mountain springs. Again I guess that is not exactly right. So, water classification, we do not need to go into that in detail, but one thing to keep in mind is that we have saline water ingressing, that is what we discussed out here earlier. Now, we are moving on to total dissolved solids, yes. So, I guess that is something that I have to rectify here. We have to look at this in that light. This is not suspended, but total dissolved solids. So, again same case here though. So, saline water, we see that the total dissolved solids are pretty high, right, and for seawater 30 to 34 gram per liter, right. Again that is 30,000 milligram per liter. So, when you have farmers having to pump out groundwater, the seawater ingresses into the coast or the inland areas, and now you have the water becoming saline, let us say. And when do we say it is saline? When its total dissolved solids are greater than 5 grams per liter, I guess, right. So, fresh water obviously much lesser, right. So, that is something to keep in mind. So, in IIT Roorkee, I guess as I mentioned, we are within what we call the good zone, but again we are somewhere around 450 or 350 though, depends on the location where we take the sample, right. And typically it is due to high calcium and magnesium which cause hardness. This is with respect to IIT Roorkee. And NCR again over exploitation of water, leading to different deposits and dissolution. That is why it is remarkably or relatively high, let us see, right. So, let us move on. In Agra poor, I guess again that is due to the quality of water there and also industries there, I guess. So, size classification, this will give a good idea, I guess. Here we have biggest particles here, sand and silt, again suspended, right. And here you have what is this, dissolved, I guess, right. So, let us look at what do we say, the relevant classifications. So, dissolved, colloids and suspended. So, here they can be settled, sedimentation, or you can act a coagulant and so on and so forth, make them form flocks and settle easily or relatively easily. They can be removed by coagulation and flocculation. We will look at that later. But this viruses and some bacteria, let us say, they cannot be removed by coagulation and flocculation, they will not settle, colloids, right. And then obviously you have dissolved, right. So, you need to look at different treatment mechanisms. So, what are the different treatment mechanisms we have out here? So, as I mentioned out here with respect to the bigger particles, obviously you can settle them, gravity. If not, then you are going to coagulate and flocculate them to make them bigger and then settle them, or you can have different filtration, well not really microfiltration here, but again ultrafiltration, sand filtration at least, and so on and so forth. Different filtration, let us say filters, right. You have different particles out here and the water as it passes through, the suspended matter is filtered out, right. So, that is what happens, right. Let me say if this is the diagram and this is the suspended matter that is being removed by the or filtered by your filter, right. So, with respect to smaller particles, as discussed earlier, we can't remove them by settling or coagulation and flocculation, but some kinds of ultrafiltration or filtration, ultra and nano filtration, and sometimes slow rate or slow sand filtration can remove them. What is it again? We have organic content, typically humic acid or natural organic matter, and then some viruses, but again not really sure with respect to viruses. But with respect to dissolved, as in trihalomethanes, which are disinfection byproducts, metals, salts or pesticides, how do you remove them now? Here you need to, if you think this is present in your source of water, you need to look at what is it, precipitation, but you can't do that in your home I guess, right, home water treatment units. So, there typically we look at reverse osmosis, let us say, right. We will look at this in relatively greater detail later on, but in water treatment plants, yes, we do look at oxidation or precipitation, not or and precipitation, right. So, let me move on. So, here we have we are done with turbidity and total dissolved solids, we are moving on to hardness. Why? I guess we discussed this earlier, but I think I have a picture here. So, here is what a typical what do we say pipe looks like, after it has been running water that is rich in calcium and magnesium. So, you have hard water buildup due to calcium and magnesium. These are the depots, let us say calcium and magnesium depots. So, that is what you see. So, obviously over time you have the failure of your water distribution network, because you now need high pressures and so on and so forth to pump water through, right. So, that is going to be an issue. But typically in some countries, depending upon the type of water and the design, instead of this level of precipitation being allowed to occur, they do allow some precipitation, maybe this level, let us say they do allow some precipitation. Why? Because they do not want the pipe to be corroded. Usually pipes get corroded after some time, but if you have this thin layer of what we say calcium and magnesium precipitates, that is going to act as a barrier against pipe corrosion, let us say. But obviously in this level of or with this level of precipitation, you are going to have remarkable effects. So, when we talk about other aspects, obviously it leads to soap scum, I guess is the term here. So, you do not have enough lather being formed, right, when you are using it for your kitchen cleaning, bathing, right, and so on and so forth, or washing your clothes. Why is that? Because this soap with the negative charge here, I guess. If I am not wrong, it has the hydrophobic and hydrophilic tail and head, but again that is for a different day. You are going to have this, that is what they are referring to as soap scum, I guess, right. So, increased amount of soap needed, scaling on pipes which we discussed, causes walls to stick, again plumbing stains and so on and so forth, we discussed this earlier, right. Total hardness is the sum of all polyvalent cations, polyvalent, right, not monovalent. So, +2, +3, so on and so forth, but typically in water we do not have +2, +3 and +4 cations, right. We typically have what is it now, bivalent, I guess. So, but practically what is it? Typically it is only the sum of calcium and magnesium, the predominant minerals in natural waters, let us see, right. So, hardness, though technically it is the sum of all polyvalent cations, it ends up being the sum of calcium and magnesium in water. And it is broken down into carbonate and non-carbonate hardness, because the way you can remove calcium and magnesium will depend upon the type of hardness that it is, I guess, right. So, again as we discussed in Roorkee, we are more or less somewhere out here, if I am not wrong, 200 or 250 or so. So, as we see, water is hard, but in most places in India it is relatively hard. Let us see, most places in India it is relatively hard. Again, please note that the units are presented as CaCO3. Right, I think we looked at it in terms of equivalents and calculations. So, we are not going to go into that in detail. So, different ways, but one way is obviously when you have what do we say surface water coming in contact with limestone and deposits of magnesium, and then being dissolved and you have release of calcium and magnesium, right. These deposits are going to be dissolved over time when they come in contact with relatively acidic waters, I guess, and then you are going to have what do we say, dissolution of calcium and magnesium. So, hardness, I guess, as can be seen here, we classify that in terms of carbonate and non-carbonate hardness, right. So, carbonate hardness, as I guess we discussed the last time we met, it was the one that typically what do we say precipitates, let us say when you heat it up. You see this in boilers, you would have seen this in your vessels scaling forming on the vessels used to heat water, right, either for bathing or drinking. You would have seen that scale formation. Obviously, after certain time, the more and more heat is required. Obviously, the scale is not a good conductor of heat, right. So, again in the same case, boiler 2, the efficiency goes down, right. Again, both industrial issues and also issues, I mean concerns faced by the common man, right. And the other one is non-carbonate hardness. So, I guess textbook wise, obviously people say this temporary hardness because heating the water will remove it, but rarely will you ever heat the water to remove hardness. But again, let us just note what people are trying to say. When the water is heated, typically you are changing the equilibrium constant, and you know that it depends upon the temperature, and again you are going to shift the equilibrium, I guess, to the left, right, and then you are going to have what do we say deposits, I guess, or precipitation. That is the principle out there, right. But another reason, or let me also discuss non-carbonate hardness and then we will come back to that. Obviously, again as we just discussed here, carbonate hardness, right, as the name indicates, is the one where the bivalent cations are associated with the inorganic forms of carbon, CO3 2 minus and HCO3 minus, right, but typically CO3 2 minus, I guess. And obviously, let us say if you have hardness, let us say calcium and magnesium, let us say this is your concentration, let us say, and if your alkalinity or such is here, all the what do we say hardness will then be carbonate hardness, I guess, right, carbonate hardness, okay, carbonate hardness. So, but obviously if it is less than that, if this is the total hardness and if alkalinity is something like this, then this portion will be the carbonate hardness, the one associated with the carbonates, and the other fraction will be the non-carbonate hardness, right. Again, just simple stuff. So, non-carbonate hardness called permanent hardness because it is not removed when the water is heated, Well, that is a very roundabout way of describing things, but we will look at why I guess it is called permanent hardness, or why it is rather turns out to be permanent hardness, and obviously it is much more expensive to remove when compared to carbonate hardness, right. So, now I guess it is associated with Cl minus, SO4 2 minus and so on, right, when the bivalent cations precipitate out with these ligands, let us say. So, again the issue here is that, as we saw, let us say take one example, CaCO3 solid will be in equilibrium with Ca2 plus and CO3 2 minus, right. So, let us say this precipitated out, right, and you want to have the reaction proceed in this direction now. So, what can you do? You can decrease the concentration of the reactants that is in equilibrium with the system, right. But obviously, how is that going to happen now, right? Or think of ways you will lead to formation of the precipitate when high calcium and high CO3 2 minus is present. So, if you want to lead to dissolution, what can you do, right? Obviously, you can decrease Ca2 plus or CO3 2 minus. The easiest way obviously is changing the CO3 2 minus concentration by decreasing the pH, right. As I think we discussed earlier, carbonate system, I think we discussed that in detail, right. This is what now 10.3, right, CO3 2 minus, and this is 6.3, right. So, when you bring down the pH, obviously now you can lead to or decrease the concentration of the ligand here, that is under question, right, and you can lead to dissolution of CaCO3, and I guess that is what you would even see in with respect to the accessories in your bathrooms and such. You have scaling. So, you can have mild acids and such that you can use to what do we say, dissolve CaCO3 or the relevant scales that are formed. But with respect to, let us say calcium and magnesium, let us say associated with sulfates, let us say, I am not sure if CaSO4 will precipitate out, but let us say we assume that, right. So, let us say this one. Now, we have that in equilibrium with Ca2 plus and SO4 2 minus. And if you look at the pK of H2SO4, HSO4, right, you know that it is either negative or 0. So, you need to bring down the pH to unacceptably low or practically unfeasible or infeasible levels to be able to reverse this precipitation, right. Why is that? Again, if you wanted to go in this way, you need to disturb the equilibrium. For that, you need to bring down the concentration of these reactants that are in equilibrium with this scalant, let us say, or the precipitant. And for that, obviously, as you see here, to bring that down, it has to be really low because the pK is pretty low, right. That is something that we saw here. So, that is again another not another reason, the reason why we typically call this as or refer to such precipitates as permanent hardness, I guess, right. And this is an issue even in your what do we say, water treatment plants and such. Let us say this is your membrane and you have this deposits on the RO membrane, let us say reverse osmosis membrane. So, what happens over time, it's your membrane is going to get choked, right, the mass flux is going to decrease. So, you have to increase the pressure a lot, so costly. So, that is the reason typically I do not like RO, because you do not need that level of treated water for most of the kinds of water that we come across, but again that is an exam question. So, we will discuss that later now, right. So, again that is one thing. So, now to remove this what can you do now? It is difficult to get rid of this permanent hardness from the surface of the membrane, and RO membranes are remarkably costly, right. So, that is something to keep in mind to when you I guess go out and set up a company and you are looking at RO membranes and such, right. Okay, so, let us move on. So, obviously, non-carbonate hardness is total hardness minus the carbonate hardness, right, the one associated with it. And obviously, if alkalinity is greater than total hardness, then total hardness and carbonate hardness will be the same and non-carbonate hardness will be 0, right, if alkalinity is greater than total hardness, right. Again different units, but again keep in mind that here we are talking about every time equivalents, let us say. Here we are talking about Ca2 plus, Mg2 plus and so on and so forth. Here we are talking about the charge here. So, obviously, we need equivalents, I guess. The units are in terms of equivalents, right. equivalents now, right. So, again milligrams per liter, different what do we say, as we know equivalents can also be expressed in terms of as CaCO3, and I think we already looked at a couple of examples in this regard, right. And I guess 2 equivalents, right, because we have what do we say, Ca2 plus out here, right, with respect to calcium 2 plus out here, right. Again that is what we have, and again general aspects which I will leave to you to read, I guess. So, here we have an example, and it looks like we have a sample of water having a pH of 7.2. I think this is from IIT Roorkee. This is the data that I got from there. Anyway, let us see. A sample of water having a pH of 7.2 has a concentration of the said ions, and you are asked to calculate the total carbonate and non-carbonate hardness and alkalinity and bar chart, I guess, but that is for understanding, I guess, right. So, let us understand what we have. We have cations here and we have anions, but again hardness is going to be due to calcium and magnesium, and carbonate hardness will depend upon HCO3 and CO3 2 minus, right, or the alkalinity, right. So, that is how we are going to calculate the carbonate hardness, and obviously non-carbonate hardness plus carbonate hardness is equal to the total hardness, and thus you can calculate the non-carbonate hardness, right. So, that is the way to go about it, but obviously the first aspect is here we have the units of milligrams per liter. So, what does this mean? Milligrams of Ca2 plus per liter of water. Here it is milligrams of or 10 milligrams of Mg2 plus for 1 liter or per in 1 liter of water, right. But now we need to have or change the units into equivalents, right. Only then can you calculate it or use it for either alkalinity or hardness and so on and so forth, right. These are relevant terms. So, what is it going to look like now? So, first the charge balance, right. If we have a good enough what do we say, or if we had an exhaustive list of the relevant ions, it should always what do we say, have electron neutrality. The water will always be electron neutral. Sum of the equivalent concentrations of the cations should more or less be equal to the sum of the equivalent concentrations of the anions. So, that is what you would expect out here, right. So, that is what you would see here. And then what is total hardness? As we know, it is the one associated with calcium and magnesium concentration. So, that is why we see this as total hardness, right. And then if it is HCO3 minus, and because pH is 7.2, will there be any CO3 2 minus? Not really, right. You know that, you have the speciation diagram, and if it is 10.3 here, pK1 is 6.3, and if the pH was 7.2, you will be somewhere out here, and you will not have any CO3 2 minus, but most of it will be in terms of HCO3 minus. So, that is one reason why we do not have any CO3 2 minus here. So, HCO3 minus and the other anions. So, the hardness associated with HCO3 minus will be called the carbonate hardness, typically with calcium, and the other fraction will be due to the non-carbonate hardness, I guess, right, both due to calcium and magnesium, right. So, let us now move on. Yes. So, hardness here, what do we have here? We have the different ions, concentration, the given concentration of the water, molecular weight, milligram per millimole or grams per mole, I guess, right. And here we have the equivalents, then we will calculate the equivalent weight, right, and then concentration in equivalent per liter, and then concentrations as CaCO3, let us say, right. I think the question also asks for the units as CaCO3 if I am not wrong, but if not, we can always understand the scenario, right. So, here n is 2, 2, 1, 1, minus 1, minus 2, minus 1, or 1, 2 and 1, I guess, right. So, again it is pretty simple out here. This is with respect to charge, obviously that is what we are looking at here. Again what do we say, equivalents here, and then equivalent weight, right, molecular weight by the equivalents. So, this is with respect to calcium. So, 40.1 is the molecular weight, and then the equivalent weight comes out to be 40.1 by n, which is 2. So, 20.5. So, similarly you will calculate the relevant what is it now, equivalent concentrations of all the cations and anions. For example, and not for example, I need to point out one aspect. Let's say in the exam, you are given data and you like me can't remember the molecular weight of, let's say, sulfate or let's say sulfur and so on and so forth. So just write a value saying that assume a value, not value variable, saying that X is the molecular weight of sulfur, and you can go ahead and do solve your problem, I guess, right? No need to think way too much about such petty aspects, right? So again, that's something that I wanted to clarify. And then concentration in equivalents per liter, that's again obviously pretty straightforward here. We have the units in milligrams of Ca2 plus, let's say 40 milligrams of Ca2 plus per 1 liter of water, right? So here we have, what is this now? The units here are milligrams per milli equivalents, right? So obviously, as you can see, you need to divide this unit by this particular one. So right, when I divide, I'll have this in the numerator milli equivalents per milligram. Milligram of Ca2 plus, milligram of Ca2 plus cancel out, and so you'll end up with not 40. What is the weight out here? So equivalent weight is 20 or 1 by 20.05. So I'll end up with equivalent concentration. So milli equivalents, that's what we have out here, per liter, that's what we have out here. So it looks like it's almost equal to 2 or 1.995 milli equivalents per liter, right? And typically, when you give the answer, I would request that you round off to 2 digits, 2 significant digits, let's say, right? So for calculations, obviously more, but when you give the final answer, please round it off to 2 significant digits unless otherwise mentioned, right? And then what else do we have? We need to have, I guess, the units also expressed in terms of as CaCO3, right? So again, here you need to have the equivalent weight. If I am not wrong, where do we have that? Okay, we have another sample calculation here. So we have 2 ways to calculate. Either you can directly calculate from here and get here, or go from here to here, right? 2 ways, different ways. Let's see what we have. Concentration of Ca2 plus in terms of CaCO3. So here we have concentration in milli equivalents per liter, right? And then equivalent weight of CaCO3, which is 50 milligram per milli equivalent. Molecular weight of CaCO3 is 100, but again N is 2, so you have 50 milligrams per equivalent, I guess, right? So that's what you have out here. And so the units here are for calcium, it's 1.995 milli equivalents per liter. And what do I have here? I need it in terms of as CaCO3. So we have 50 grams of CaCO3 per equivalent, right? So obviously, if I need the units in terms of that, I need to multiply it by 50 grams of CaCO3 per equivalent. So equivalent cancel out, and I guess I end up with 99.8 milligrams of or as CaCO3 per liter. Equivalent cancel out, so milligram per liter, right? Milligram as CaCO3. So similarly out here we have what do we say, the different what do we say, those concentrations in terms of CaCO3 now, right? So let's, I guess, calculate hardness, or okay, first check how has to be with respect to ultra neutrality or charge balance. So here, I guess, when we do it in terms of equivalents per liter, so looks like have 175.6. Did we do it in terms of equivalents? Well, let me just make, okay, in equivalents, I guess this, because this value would be much higher. Okay, 175. Well, this can't be 175, though this 100, 140, 165, let's say, okay. I guess so. 60, 90, 150. Okay, so it's obviously the units in terms of as CaCO3. Okay, here it is. So again, we can also check it in terms of equivalents per liter. So we see that there is electron neutrality being held, but typically you will not have such exhaustive data. right, and then we will move on to calculating total hardness, which is the sum of the polyvalent cations, and typically it is going to be calcium and magnesium. So, in terms of what do we say, milligram per liter as CaCO3. So, we see that this is the hardness, and this is typically on the lower side. In let us say in Roorkee, we typically have 250, in other parts of India relatively higher, I guess. And I guess alkalinity, we know that this is the what do we say, expression. Please note the brackets. This means in terms of the concentration of the relevant what do we say, variables or compounds here have to be in equivalents per liter. If it was the square brackets, then we would have had to have plus 2 times for CO3 2 minus. Why is that? Because it contributes to 2 charges, or rather here in terms of alkalinity, CO3 2 minus can neutralize 2 H plus, right. So, that is something to keep in mind. So, here okay, looks like I already have this on the slide out here. So, units of ions are in equivalents per liter, and units of ions are in moles per liter, right. So, pH is 7.2, but what do we know at 7.2? OH minus and H plus are more or less the same, you can cancel them out. We know the pKa, so CO3 2 minus will be negligible at what do we say, 7.2 pH. So, alkalinity will more or less be equal to HCO3 minus, right. So, and that is what I guess we see out here, and looks like the concentration of alkalinity in equivalents per liter is 1.8 into 10 power minus 3 equivalents per liter. So, again we are multiplying it with I guess the equivalent weight for CaCO3, and then we have it in terms of alkalinity in terms of or as CaCO3, right. And what do we have? I think this was 140 total hardness, and the carbonate hardness we have around 90, is it? Yes, 90. So, obviously 140 minus 90, the 50 is going to be equal to the non-carbonate hardness. So, let us see carbonate hardness. So, it is the same as what is it, alkalinity. So, and total hardness is calcium plus magnesium, and then obviously non-carbonate hardness is going to be the difference. So, that is I guess equal to 50.9 milligrams per liter as CaCO3, right. So, now we are going to move on to other parameters, dissolved oxygen, BOD and COD. So, one reason for I guess again sharing these values is that you need to be knowledgeable about, or the expectation is that you will be knowledgeable about what you can do and probably should not do to harm the environment around you, and also to allow you to take a knowledgeable decision when faced with scenario, let us say, or A and B, let us say. In this context, typically most applications can be understood in terms of these variables. So, that is why we are looking at these variables, right. So, here we have dissolved oxygen, biochemical oxygen demand and chemical oxygen demand. So, first it is why do we need to care about dissolved oxygen? Again it is dissolved oxygen, right, oxygen in the aqueous phase. So, what are we concerned with, or why am I as a selfish citizen concerned with it now? Again I am dependent upon air and water, right, air every second, water now and then food, I guess, right. So, anything in the air is going to continuously affect me. So, the effects are going to be relatively what do we say, pronounced, if I may say so. And with respect to water, similar aspects, let us say. So, you want your water bodies to be relatively healthy, and for water bodies to be relatively healthy you need thriving aquatic systems. They keep the water bodies healthy, if I may say so, right. And for most organisms are depend on oxygen, right, for their metabolism. So, you need, or they need, dissolved oxygen. So, dissolved oxygen, when there is no dissolved oxygen, let us say, what happens, this is what you see, mass fish kills, I guess. There are other aspects, but obviously I am trying to highlight some of the more extreme events which are now occurring relatively more frequently, right, those events that can catch your eye. So, here again the article is from the Hindu, which I typically recommend, and here I guess we are talking about Ulsoor Lake in Bengaluru, but this can be the case in any lake, most lakes, if they still exist, let us see. So, hundreds of fish found dead, they bloat up and then start floating up here, and you have these hundreds and hundreds of fish kill. Other than them or the dead fish polluting the what is it now, water, typically dead fish indicate an underlying issue, then typically it is because of dissolved oxygen fluctuations, let us say, especially in the night, let us say, or during low temperatures now, not low, high temperatures, right. So, again we will look at that later. Dissolved oxygen, and again here we have fish kill again in Ulsoor Lake, and do I have the link, another link. As you see, this is one particular article, again another article again about the same what do we say lake. Again maybe some information from the article here. The site of fish kill, the authors think, or the journalist thinks that the site of the fish kill has some answers to what caused the fish kill. He thinks that heavy dumping of solid waste, well including non-biodegradable plastic and wet waste, by the residents around the lake, let us say, is leading to the deaths, let us see. And though the lake is said to be one of the better maintained lakes in the city, it suffers from inlet of or ingress of untreated sewage. Sewage means human feces and so on and so forth from into the lake from surrounding areas, which also leads to increase in the ammonia levels in the water. Sewage water is responsible for depleting the dissolved oxygen levels, causing repeated fish kills. Again fish kills, and also it will kill almost most of the aquatic life, I guess. So, what is happening here now that you are relatively more knowledgeable. So, but you will know that again as we go through the relevant material or understand the system. First, when we say untreated sewage coming in, or maybe let us say some wet waste, you are talking about kitchen waste, let us say they are relatively reduced forms, let us say, right, and they can be oxidized, right, or mineralized. But what do they need? Obviously, they need an electron acceptor, which is oxygen, right. And obviously, your waste or your feces is competing with the oxygen in the water. So, the fish, let us say, are also depend upon oxygen. The aquatic life is depend upon oxygen, this dissolved oxygen. So, without aquatic, what do we say, not aquatic, pardon me, dissolved oxygen or aqueous, what do we say, oxygen, you are going to have collapse of the aquatic system in and around the lake, right. So, again Periyar, I guess, I think this is from Kerala, again relevant link. Again keep in mind that there are numerous instances everywhere, and this affects the quality of life of the people all around the relevant water body now, right. So, again dissolved oxygen. So, in that case you will need to understand or keep an eye out for pollutants and such that can affect dissolved oxygen in your surface water bodies, right. And it is critical to maintain sufficient levels of DO because you want to maintain or sustain the aquatic ecosystem, and typical levels that you want are 4 to 5. In Yamuna it is 0. So, that is something to keep in mind. That is why the river is a dead river, and it leads to remarkable levels of not remarkable, considerable issues, I guess, right. Let me temper myself, let us say, right. So, again DO is the minimum that will support, and then if in good fishing waters it is 9, but rarely do we ever see this, but maybe in the upper reaches or lower reaches of the Himalayas or such we can come across 9 ppm, but typically 4 to 5 is what we want to maintain, right. Again below 1 to 10 for a few hours, large fish kills, right. So, oxygen demand, right. We were talking about BOD, biochemical oxygen demand, and COD, chemical oxygen demand. So, let us see why we are looking at it, or let us understand what they are and then see how they are relevant to you, let us see, right. If you are thinking of dumping something down the drain, maybe you will rethink what do we say, your decision once you understand these aspects. So, sewage, which is typically dumped untreated into surface water bodies in India, obviously exerts an oxygen demand. That is something that we looked at in the previous slide. So, we are trying to get an idea about oxygen demand by measuring parameters like BOD, COD and theoretical oxygen demand, let us see. So, why, I guess, well, it is obviously an indirect indicator of the organic content in the water that can consume oxygen, let us say, right. So, it is obviously again an indirect indicator of the organic content in water, let us say. Organic content, typically where is that coming from? That comes from humans, again typically pollution that is being treated, not treated, given out into the water, let us say, right. So, that is one aspect to keep in mind. So, we obviously try to limit the organic content in treated waste waters. So, oxygen demand, again this is something we discussed, so I will skip this. So, it is typically the amount of reduced organic and inorganic matter in waters, and it relates to oxygen consumption in the relevant surface water body, and we can measure it in terms of biochemical oxygen demand. So, again the key is biochemical. So, it is the amount of oxygen consumed by microorganisms in converting all the biodegradable organic matter to carbon dioxide, water and ammonia. Keep in mind, but this is for what do we say, a technicality, I guess. We are not talking about nitrate or such, but with respect to ammonia, let us say. So, you have C, H, O and N, let us say, right, and you have oxygen, let us say, and that is going to lead to CO2 plus H2O plus. So, right, thus for this reaction the amount of oxygen required, that is your biochemical oxidation demand, but only if the compound is biodegradable, or only if the microbes can degrade it, let us say aerobically. So, that is the one that is called biochemical oxygen demand. With respect to COD, let us say, but again this test will take 3 days, but relatively cheap, or even 5 days depending upon the temperature you maintain it at. Temperature is key because kinetics depends upon temperature, and also you can do this at home with just a simple DO meter. You can do this at home, so you can measure the quality of your surface water body. So, that is something to understand and keep in mind, but you do not have the time, let us say in labs or such, you need data immediately. So, you can do this test within 2 hours or 3 hours, right, and it is called chemical oxygen demand. So, obviously as we can see here, we are missing the term biochemical oxygen demand, right. So, it is the amount of strong oxidant in oxygen equivalents, obviously, because we are talking about oxygen demand. So, strong oxidant which is consumed in oxidizing the relevant compounds, both organic and inorganic typically, or both biodegradable and non-biodegradable, to the same what do we say products as earlier, carbon dioxide, water and ammonia. So, typically in the lab the strong oxidant used for chemical oxygen demand is dichromate, let us say, right, that is the strong oxidant, and then we transform the units into oxygen equivalents, and that is when you get chemical oxygen demand. So, theoretical oxygen demand, I guess, is, as can be seen, is the theoretical oxygen demand required to convert the material to carbon dioxide and water. So, you can see how it differs from COD and BOD, right. Here we are only saying that CO2 and water are the final products, but in cases where organic matter contains compounds, the end product is ammonia. Okay, so it is relatively similar. So, I stand slightly corrected, right. But typically we rarely do we look at this, we typically measure this because we want to know whether the bacteria can degrade your waste, or if it is remarkably non-biodegradable and will persist in the nature. Let us say you have very low BOD and high COD, what does that mean? That means that the industry is discharging waste into your water body, right, that is not going to be degraded by nature or by microbes, and you will end up what do we say feeling the effects of this pollutant, let us say, right, and that is the case in lot of our surface water bodies. Only now is the situation changing, but again an informed populace is what we are looking for here. And one certain thing is that with the shutdown of industries, what do we say, aquatic life thrived, the people had better access to quality water. At least this was the case in Karnataka. Those were the reports that I was reading. Was it Kaveri or another river or a tributary of Kaveri? I am not sure. But this particular farmer could now use the water for irrigation, which he could not earlier. Again, that was because the industries were shut down. So, I guess I am out of time, and before we dig deeper, I guess I am going to end my session, and we will continue these aspects in the next session, I guess. Thank you.